All right, folks. Great to see you again. Not really. I'm not seeing you. Hopefully, Thursday went well and you got your questions answered on that review packet. Of course, wanted you to work hard on that, understanding what to do. I know some of those questions can be kind of tough. If you didn't quite get that finished, or you didn't quite get the chance to watch that video and check your work, go to it now and check your work. Or work with your row partner on getting through it. But right now I'm going to walk you through some of the infinite geometric series. Just talk you through it. First, there's two things. Infinite geometric series, it goes on forever. Forever. Okay, and if you have an infinite geometric series, say we start at 2 and we multiply by 2 each time, so we go up 2 to 4 to 8 to 16, we keep going. This series is not going to have a sum. It's not going to end. It's going to keep larger. If we add these terms in between, if we add that series, the value of that series at the end when it goes on forever is not going to end. But what's interesting is if we do excuse me, if we do have a geometric series where the multiplier is actually a fraction, check to see what happens. So say I start at 256, and the multiplier that I use, or the common ratio, is 1/2. That's going to go to 128, and then it's going to go to 64, then it's going to go to 32, then it's going to go to 16, then it's going to go to 8 and 4 and 2 and 1 and 1/2 and 1/4 and 1/8 and 1/16. And notice how the things, the subsequent numbers in the sequence are going to get lower and lower and lower. So if I turn around and add that, if you kind of notice how this is going, if we add this to infinity, if that keeps going, we keep adding these numbers, the next number that we're going to get is going to again be kind of a small number, again even smaller, as far as a small fraction, and then it's going to get a smaller fraction, and a smaller fraction, and a smaller fraction, and this series is actually going to converge on its way to getting a fraction that's really, really ridiculously close to 0, but it's never going to get to 0, but it's going to get really, really close. And that number, as it goes on forever, gets so small that eventually this whole series, when you add it up, is going to converge to a single number, and we call that that we have a sum of an infinite series it's going to reach a particular number when the ratio is between, and this is what this statement, if the absolute value of the ratio is less than 1, that means essentially it's going to be between 0 and 1. It's going to be convergent, which it means it's going to converge to a very specific number if we add up all those terms as we keep going. If that ratio, that common ratio is like 2, when the absolute value is greater than 1, it's going to keep getting larger and growing each time. So when we add up all those figures, the sum of it is going to keep going. It's going to have this one, the first example, that's not going to have a sum of that. That's not going to have a value for the sum of that. But this one, since we have a ratio that's whose absolute value is less than 1, we're going to have it's going to converge to a very specific number as it goes on forever, because each subsequent number within that series gets smaller and smaller and smaller and closer to 0, to the point where it's negligible when we add the next value. Alright, so that's where we get this formula for the infinite geometric series. The infinite geometric series is this, the sum of a geometric series as the limit of n goes to infinity. This goes to a very specific value, which is entailed this one right here. All right, so let's go on. This one's going to have a sum because it keeps getting smaller and smaller and smaller and smaller, because the ratio on this one is going to be 1/2. All right, so number 1, find the sum of the terms of the series. The ratio on this one is going to be, what are we doing? We're multiplying by negative 1/3. And it's going to get smaller, This one's going to have a sum. All right, so yet again, we're going to use this new formula, S equals A sub 1, which is going to be 6 from the problem, 1 over 1 minus the rate, which is negative 1/3. And we just calculate that out and make sure you get that straight away in your calculator and get the right number. Alright guys, when we calculate this one, the sum of all these terms onto infinity is going to be 4.5. Alright, next one. Sum of an infinite geometric series is 36, and its first term is 12. So let's translate this. So we have s is 36, first term a sub 1 is 12. So with the formula, we get 36 equals, and then the formula goes a sub 1, which will be 12 times 1 over 1 minus r, and the question is find the common ratio, so we're finding what r is. So we just need to solve this for r. I'm going to multiply by 1/12 so that and that reduce, or yeah, then that reduce. So 36 over 12 is going to be 3 equals 1 over 1 minus r. Now we're going to solve this for r. To get rid of the 1 minus r in the denominator of a fraction, we're just going to multiply both sides of the fraction by 1 minus r. It goes away, so we get 3 times 1 minus r equals 1. Distribute 3 minus 3r equals 1. Negative 3r equals negative 2, r equals 2/3. Woo! And by the way, if that was more than 1, absolute value that was more than 1, you know you messed up, because then the sum, it wouldn't have a sum, because it says it's an infinite geometric series. Alright, sum of an infinite geometric series is 10. So s equals 10. Common ratio, r is 3/5. Find its first term. Find a sub 1. So let's put in the formula. 10 equals, first term, we don't know. 1 minus 1 over 3/5. So we just solve this formula. We calculate that and we get a value for it. Alright, from this section we get 5/2 times a sub 1 equals 10, and we're going to multiply both sides by 2 over 5 to get rid of it, all that good stuff. So then we get 4 equals a sub 1. Done. Barbecue pork. Alright, let's go to the next one. Alright, evaluate the following if they exist. First we got to see if it's geometric first. So that times that, okay, 1 to negative 2. That's going to be ratio times the negative 2. Then negative 2 times positive 2, so this is going to be times negative 2. 4 to negative 8, that's going to be times negative 2. 8 to 16 times, okay, so our ratio is going to be negative 2. Now, this one's, we're essentially adding all these or subtracting these when we're finding the sum of this sequence. It's infinite because it's going to keep on going on forever and ever and ever. But if you notice, that common ratio is negative 2, where the absolute value that is greater than 1, so this does not exist. Sum does not exist. Alright, let's look at B. Now at B, so 1 to get to negative 2 is times by negative 2. And then we times by negative 2. Then times by negative 2. Okay, and we keep going blah, 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 and we're going to have that common ratio. But we end up stop at 10, 24. So we need to pause. This one's not infinite. Holy cow, this one's not infinite. Holy cow. Oh my gosh. Oh my gosh, this one is not infinite. Oh my gosh, it's not infinite. Oh my gosh, oh my gosh. Alright, that was me having fun with you guys when I'm not here. By the way, since it's not infinite, we need to go back to the sum of the first n terms of a geometric sequence. That's what we need to do. So we need to go back and we need to get this formula written down from up here. A sub 1, 1 minus r. So we get a sub 1 and times 1 minus r to the n over 1 minus r. And then we're going to start dropping some stuff in. So s sub n, we don't know what n is for that, which is kind of annoying. So a sub 1 is 1. 1 minus the common ratio, which is negative 2, to the n power. We still don't know what n is. And then 1 minus negative 2. So I'm going to simplify this a little bit. I know we don't know what n is, but we don't really need 1 in there anymore, because 1 times anything is just that, well, that anything. And you can't do this negative negative right there, because you first have to do that exponent. But you can do this 1 minus negative 2 being 3. But you have to do that exponent before you do that negative negative in there. So what we need to do is we need to go back to the other geometric formula, and we need to find what n is when a sub n is 10, 24. Now we did pretty much the same problem a little bit different though, I suppose. So that's negative 2 n minus 1. So 10, 24 equals negative 2. We can get rid of that 1 just because we don't need it. Log. Alright guys, so this gets to be interesting. If you go to log both sides, you'll get a no real answer, log base 2, which is kind of how we did it in class yesterday or on Wednesday. But you will notice, one of my students mentioned this, which was interesting, is you can raise that to the 10th power. And check this out, guys. Notice that we can make that negative 2 to the 10th is also 1024. Do you guys notice now that we have the same base that we can do 10 equals n minus 1, which is pretty cool. So n winds up equaling 11. So then we can put 11 into the sum of the first 11 terms. That was a 2, wasn't it? All over 3. And then we just calculate that. So the sum of the first 11 terms in this case is going to be 683. Woohoo! Alright guys, also for the interest of time, we're going to skip this stuff. We'll come back to that after the quiz. So that's not going to be on your quiz. But we'll come back a little bit later on that. Alright, pendulum problem. Here's the deal. Pendulum swings 10 feet going left to right. It goes left to right, and it swings 10 feet on the first swing. On its return swing back, it goes, on the return swing back, it goes 90% as far. So it's 10 times 0.9. And then the next one, it goes another 90%, so it's 0.9 times 0.9. If you guys notice that that's really 10 times 0.9 to the second. Also notice that this is the first, that's the second, that's the third. Notice this exponent right there. Notice that exponent's 2. It happens again, back and forth, so it's 10 times 0.9 to the third. We're just going to keep the pattern on the fourth thing. If you notice, that's a geometric swing. So if we're going to find that, and it's technically could do that infinitely, so it's going to be an infinite geometric series that we're actually looking at, where 0.9 is going to be the rate and 10 is the initial value. So we actually have this kind of set up here, where it's going to be where the initial one is 10 and the rate is going to be 0.9 to the n minus 1 power, representing each one of the swings. There is actually a sum to this, because technically if there's no friction based on wind or anything like that, it's going to swing forever, or the pulley doesn't give you a resistance, it's going to swing on forever. So we can use the sum of an infinite geometric series to find out how far this pendulum actually swings. S equals 10 times 1 over 1 minus rate was 0.9, and then we can calculate that value. Alright, now that value winds up being 100. Woohoo! That's how far it swings as it goes back and forth. Now, if we do it, if we want to know how long it takes to do 50% of the travel, 50% of 100 is 50. So we want to know how long it takes to go 50 for the sum of n to be 50, half that distance. So we're going to use the formula for S sub n, which is going to be, we're going to need a sub 1 times 1 minus r to the n over 1 minus r. A sub 1 in this problem was 10, so we're going to put 10 there. R in this problem was 0.9, so we're going to put 0.9 in there. And then we need to solve that for n. You'll notice we can subtract this. We can't subtract the numerator because we have that exponent we have to deal with first. So let's simplify this up a little bit to the n power. We can't simplify anything in the numerator, but we can in the denominator. So, and then I'm going to start digging it out. So I'm going to divide by 10 on both sides, so we get 5 equals 1 minus 0.9 to the n over 0.1. I don't need those parentheses anymore. And I'm going to get rid of that fraction, so I'm going to multiply by 0.1 on both sides, and it's going to get rid of that fraction. So it's going to be 0.5 equals 1 minus 0.9 to the n. Alright, then I'm going to subtract 1 from both sides, and we're going to get negative 0.5 equals negative 0.9 to the n. Divide by negative 1, 0.5 equals 0.9 to the n. And now I'm going to turn around and log base 0.9 both sides to get rid of that base right there. So we get log base 0.9 of 0.5 equals 9, and we calculate it in our calculator, and we get approximately n equals 6.58, which is going to be after which swing, so it'll be after the 6th swing. Alright guys, email me if you have any questions or have any struggles. Of course, I know I blew through that last question pretty quick because I only have 50 minutes of recording time. Anyways, email me as soon as you have questions, and I'll be more than happy to answer those. We'll see you guys back on Monday. Hopefully you have a good weekend. We'll talk to you later. Bye.